Let's now learn about what a sampling distribution of a proportion is. So we start out by looking at the following question. What is the true proportion of left-handed people in the world? And so for now, we don't need to be too worried about the term true proportion. But what I found here is in a group of people, mainly my students when class was still face-to-face, then in a group of 15 students, I noticed that about 4 of my students were being left-handed. So being left-handed here means they did not only write with their left hands, but also they naturally pick up an object by a left hand, or they have the tendency to use the left hand more than the right hand, and that's what the left hand is being considered as. So being a proportion, we quite usually put that as a decimal in 4 decimal places. And so in this case, calculation comes out to be 0.2667. So now we thought this is the proportion. This is a proportion, or the proportion. We thought this is the proportion of left-handed people, and for short, just left-handed. But so now the big concern, and the reason I'm putting question marks here, is that does this reflect the true proportion? And so now allow me to explain what true proportion means. The world is not only having 15 people or 15 students. Admittedly, I found a proportion, some proportion, reflect my left-handed, but this proportion is only reflecting what's happening within the group that I was looking at. But in the end, anyone who views this video can well realize that this answer can no way be regarded as the answer to this question here. And so this true proportion, the answer to that is intended to be a population proportion. And a population proportion has the symbol, carries the symbol lowercase letter p. But then looking back at this answer we found here, so we cannot regard to this as that true proportion. So what about this proportion? We did find some proportion of the left-handed, but it's only limited to a small group of 15 students, of 15 people that I looked into. And so instead of being the true proportion of left-handed people in the world, this is some proportion, but it only deserves its place to be a sample proportion. And unlike being a population proportion, for sample proportion, we use a lowercase letter p as well, but with a hat to indicate what we have here, either in fraction expression or as a decimal in 4 decimal places usually. Then this is only a sample proportion. So from now on, a lowercase p with a hat is a symbol for being a sample proportion, whereas a lowercase plain letter p is a population proportion. So now back to this question. What is the true proportion of left-handed people in the world? The intended answer for this question is apparently not the true proportion here. Apparently refers to the population, because the only way to find a true proportion of left-handed people in the world is to search through the entire population, count the number of left-handed people, and come up with this, what I so-call now population proportion. That's the intended answer for this question. And as a reminder, so population proportion is now agreed is to have the symbol lowercase letter p. What we have found in a group of 15 students, 15 people, 4 of them are left-handed, and this is a proportion. In decimal, it was 0.2667, but this was unfortunately only a sample proportion, because this group of 15 people is nowhere big enough to be considered as a population. The world is not only having 15 people, and so the better place for this proportion, it is a proportion, but the better place for this proportion is to be regarded as a sample proportion, where the symbol for this is a capital P hat. And so at this point, after so much argument, after so much explanation so far, we still have not found the answer to this population proportion. In other words, it remains a mystery. The answer to this question remains a mystery. But now, anyone who have seen this video of mine on sampling distribution of a proportion of the proportion, then I highly recommend watching this video lesson after watching the video lesson on sampling distribution of the mean, because the idea is extremely similar. So looking into these this sample proportion, it came out from a sample. So let's look a little further into this. But so 4 out of 15, we can regard to the group of 15 people as the sample size being 15. So it's the way how we find any proportion. Simply a proportion is simply coming out from setting up a category. So here we're looking for the category being left-handed people, and so we search for a group of people, and we call that small group that we searched, that we collected for, is to be a sample. And then within that sample, the successive count right here, the successive count reflecting the number of people falling into the category in our sample is and putting that number, the successive count, over the total number of people in our sample, we have for ourselves the sample proportion. And in decimal, this is a 0.2667. And so this is sample size. And the idea I would like to reinforce now is that it's very similar to collecting samples to obtain sample means. Then here we are collecting samples to obtain sample proportion. So this is, I have to make clear for everybody who views this, for anybody who views this video, but as anytime we can have a sample, then there will be another one, and there will be another one, and there will be another one. And so right now I can regard to this sample of mine here as how about, let's call this simply just sample 1, because it happens to be the first sample that I brought up. And so this sample proportion value came out from sample 1. Now allow me again to use a subscript attached to this lowercase letter p with a hat. So lowercase p hat 1 is indicating that this is the sample proportion value limited to the sample 1. And so now let me have everybody's attention on the computer screen I have here with Microsoft Excel, where I have recorded a few more sample proportions. So the idea is we're gonna remain on sample size n equals 15. But let's look at the screen on with my Microsoft Excel file right here. What I have done is I have made a collection about a few samples. So just like I said, once there can be one sample or a sample, then there must be other samples. Some other students in my past quarters contributed these samples for me here. So some students searched among their relatives and their friends, and 15 people there for this. In this sample, for example, I found 2 of them being left-handed. So here, according to the Microsoft Excel file, I can have a sample 2 where sample size is being 15 again, and the sample proportion here was out of 15 people being collected there, only 2 of them. So the successive count changed differently this time, and this is I can regard to this as a p hat, lowercase p hat 2, and of course in decimal this is 0.1333, and usually for the rest of the quarter, usually any time it comes down to proportion, it's most of the time I use 4 decimal places as the decimal expansion of any proportion value, including population proportion and sample proportion values. So sample 2 gave us a sample proportion being 2 out of 15, or in decimal 0.13333. And so just like that, let's have everybody's attention again on my computer screen here. And so this Microsoft Excel spreadsheet that I have here has a few more samples. So I have to admit that this collection of samples here is nowhere enough to compare to all samples existing out there, but it's enough to illustrate the idea that there should be infinitely many sample proportions. So there are infinitely many more p hats values, sample proportion values. And here on my Microsoft Excel screen, I only had about 9 different sample proportions, and some sample proportion can be equal value with some other sample proportion, but they are not necessarily the same sample. That could be the different group of 15 people, but the successive count turned out to be just the same. And so here I just now put in a third sample, and here is the value of the third sample proportion here. And once again, the idea now is that as long as we can find one sample, then there will be another, and there will be another, and each of these samples gives us a sample proportion, because that's what we are looking for in a sample. So the question again being addressed here is that how many of these samples can there be? How many of these sample? And of these samples, I mean the sample proportions. Can there be? And how about let's get general at a given sample size. So you can see that all of my sample proportions that I am illustrating here in my lecture currently, I'm staying at the given sample size being 15. But here, how many of these sample proportions can there be at a given sample size? At a given sample size n. And so I briefly mentioned earlier, but the idea now is that there are going to be infinitely many more sample proportions that's waiting for us to collect here. So we don't have to search through all sample proportions, but the answer to this now is clearly there are a lot. We don't need to know how many, and as a matter of fact, formally speaking, infinitely many. That's just to describe how many. So many of those sample proportions to the point that we don't really need to find all of them. We just have to realize and keep in the back of our mind that anytime that we're in the world of collecting samples, there's not only one sample. There are many other samples, provided they're all in the same given sample size. So upon realizing there are that many samples, there are infinitely many samples, then once again, very similar to the time that we were learning about sampling distribution of a mean, then I'm now going to circle all of these sample proportion that we're looking at here. Okay, and so the reason I'm circling these now is that all of these infinitely many sample proportions together as a huge set of values deserves its place to be a, what we can understand here is this is truly a population. A population of sample proportion values. So it's a population of p hat. So like I said, we have an infinite number of samples, 15 people, 15 people, and 15 people, and every one of these 15 people as a sample has for themselves a successive count of how many people in each of those groups being left-handed. So all of these sample proportions together can become a population of sample proportions. And or sometimes we might refer to this as it's a distribution. A distribution. To make the term a little more formal in statistics, it's a distribution of sample proportion values. The reason I say the distribution because maybe some of these values of sample proportion can have more probabilities, and versus some other values is having less probability, less likeliness. So all of these, so this entire population of sample proportions, or the distribution of all sample proportions here, we have the formal term now is called, so what we have here is regarded as the sampling distribution. Sampling distribution of the proportion. So generally speaking, the sampling distribution of the proportion is just a population of all sample proportion values. So here specifically in this question that I brought up for here, then the proportion we're looking at is the proportion of left-handed. And so this is one sampling distribution of the left-handed proportion. And then when we change to a different sample size, then there is a different sampling distribution, but of the same proportion of the left-handed. And later on throughout, as I go through the later examples, then we are going to be working with different sampling distributions of the different proportion. And so we are now ready for a formal definition of what it means by being a sampling distribution of the proportion. So a sampling distribution of the proportion. So a sampling distribution of the proportion is the population or sometimes we refer to this as a distribution. It should have been is a population or a distribution of sample proportion values at given sample size, capital N. And then quickly briefing the idea, but once again, p hat, the major idea that we derive this definition is because p hat, any p hats, a p hat value represents the proportion p. That's one idea. There is not only one p hat value. There are infinitely many. P hat values. And that's why it deserves its place to be considered as a population of p hats. And we must agree that all samples in each distribution have equal sample size, equal given sample size. And so now realizing that at given sample size being 15, we can have infinitely many p hat values, sample proportion values, and there are different values there. So it's now a good time to introduce a random variable, because what we have here, as we already have agreed, that what we have here is a population of sample proportion values of p hat values. So let's now come up with a random variable to represent any of these values for a sample proportion, because here a lowercase p hat 1 is only a sample proportion designated to this particular sample 1. This 15 group of people is different with the other 15 group of people. Some of these sample proportion values might come out equal value, but in the end they're all different samples once again. And so these are lowercase p hats 1, lowercase p hats 2. These are specific sample proportion value limited to any particular sample. But now generally if we regard to any of these values, then we must give a random variable. So the random variable we're going to define here. So as the random variable for this to represent sample proportion, then being a sample proportion generally is a p hat, but here being a variable, a random variable, I'm now going to start using a capital P hat. So a capital P hat is to represent the proportion in a sample. But then specifically in my style, and I believe that I am the only one in doing this, but I'm going to introduce the sample size as a subscript. I am going to attach to my random variable here the sample size n as a subscript to indicate, so any value to this random variable is the proportion in a sample of n individuals. Okay, so meaning if we apply this understanding into this particular sampling distribution of our proportion here, then all this here, any of these value here, I can regard to this as a general random variable capital P hat, where sample size is 15 on each. Or in other words, particularly in this study about the true proportion of left-handed people in the world, and each of these values is a sample proportion of left-handed people from a sample of size 15. Then generally capital P hat 15 in our study here is to represent the proportion of left-handed people in a group of 15. And again, let me explain that when I introduce the random variable with the sample size as a capital letter N being attached to the random variable here, or as one random variable, it actually creates for me a good advantage to distinguish among the many different sampling distributions. So let me bring up a quick demonstrating example as following. So now in my style of naming the random variable, then we have seen capital P hat 15, and there will be other times that we're working with maybe capital P hat 300, for example. But so capital P hat 15, and provided we're still talking about the proportion of left-handed people, so a capital P hat 15 means each of the values this random variable takes is the proportion of left-handed. And allow me to go brief a little bit. So capital P hat 15 is the proportion of left-handed in a sample of 15. Underline this sample of 15 right there. Whereas same study about left-handed proportion of left-handed people, but if I now use the random variable capital P hat subscript 300, this means each value that this random variable will take means or represents the proportion, almost identical meaning, the proportion of left-handed but then in a sample or in a group of a sample of 300. And so this is a sampling distribution of the proportion where each sample, it's clearly indicated here that each sample has only 15 individuals, whereas this is another sampling distribution of the proportion, a sampling distribution of proportion of the proportion as well. But what's indicated clearly here is that in each sample here contains or has 300 individuals. And so apparently under this argument of mine right here, I would like to argue my point that these two, this sampling distribution and the other sampling distribution, they are clearly two different sampling distributions. of the proportion. There are two entirely different populations of sample proportions. And so now, at this point, we well realized that at any given sample size, and here in this case, sample size equals 15. And so for any given sample size, then we can have one sample proportion value, and we can have another sample proportion value, and we can have another sample proportion value. And as a matter of fact, we can end up with infinitely many more sample proportion values, all with the same sample size and equals 15. To the point that, again, just a reminder, this is a population of sample proportion values, lowercase p hat values. And particularly in this quick little example I'm having here for the proportion of left-handed people, these are the sample proportions of the left-handed people, then we already understood that this can be assigned with a random variable capital P hat 15. The question to be addressed now is that, can these infinitely many sample proportions here, can all of these be averaged? So can these p hat sample proportion values be averaged? And so the simple answer is yes, we can. Yes, they can be. Yes, they can. So if we average out these sample proportions, in particularly here in our case here, sample size 15 in each of our sample, then once again, if we average out all of these sample proportion values here, how would we do that? Well, then we have our p hat 1, in this case being 0.2667, or we can stay with that with the fractions. We're going to take our p hat 1. We are going to add with our p hat 2 values, where we can go with decimal being 0.1333 or 2 out of 15. Then we add with our sample proportion number 3 being 0.4 in decimal or 6 out of 15 in fraction. And we keep adding up, and we add all of the sample proportion values that we can ever end up with. And here, of course, without knowing how many there will be more out there, I'm going to leave dots here. But the idea is, once we can achieve adding up all sample proportion values of sample size 15, as we are looking at here, then we are the way and the only way to find mean value, to find average values, we're going to need to divide by the number of all samples there are. And the number of all samples there are, I mean a number that is a lot more than only 3 samples here. So on my board, I'm only able to show 3 samples, but there are infinitely many more. And so if we can add up all sample proportion values and divide by the number of all samples existing out there, then this is that average that we're looking for. And so yes, we can average the sample proportion value. And in the end, as a reminder again, that all of these sample proportion values together become a population of p hat value. So this mean value that we're attempting to get here makes sense to be a mu again. It's the mean value, but it's the mean value of all sample proportion values. It's a mean value on the population of sample proportions. So in this case, now allow me to introduce a new symbol. This is what I call the mu p hat. This is the population mean of all sample proportion values. So generally speaking, if we use a capital letter p hat with a subscript n to represent the proportion in a sample, the proportion value in a sample of size n, then this, in other words, represents a population of p hat value of lowercase p hat sample proportion values. So that means we're looking at, so once this random variable is defined, then there is an entire population of p hat 1 value, p hat 2 value, p hat 3 value, an entire population of p hat value. And here I'm using the general sample size here. And so mu p hat is the population mean of the p hat population. How's that? And this p hat population, in other words, this is the mu p hat here. In other words, mu p hat, in other words, is the mean of the sampling distribution of the proportion. And again, it is important to re-emphasize that mu p hat is, as a role, it is the center of the sampling distribution of the proportion of the sampling distribution of the proportion. So in that way, in that argument, then once we found the center on any sampling distribution of a proportion, then the next thing we're heading out for is there's an average spreading. And so now also allow me to introduce for the first time sigma p hat value. So sigma p hat value. So think about on any sampling distribution of a proportion, of the proportion. And after we have found a center, then there is an average spreading. So formally as a name, sigma p hat is the standard deviation. Standard deviation of the p hats population at any given sample size. And then as a role, sigma p hat on And of course, the p hat population here is, in other words, the sampling distribution of the proportion. But then thinking as a meaning, as the role of sigma p hat after we found mu p hat, then sigma p hat is playing the role of the average spreading. It's indicating the average spread, how sample proportion values are on average spread it away from the center once we found it. So sigma p hat is the average spread or average spreading of the p hat population, or in other words, again, the sampling distribution of the proportion. Sampling distribution of the proportions, sample proportion. This is also the same. Sampling distribution of the sample proportions value. And further, this distribution of sample proportion values at a given sample size n, just like any other distribution of values out there, this distribution will also have a distribution shape. So in other words, or generally, capital P hats of n has a distribution shape. So think about once you put all sample P hats that you can ever possibly find into a histogram, then you're going to recognize some kind of distribution shape. So the distribution shape for any sampling distribution of the proportion can sometimes be a, let's say once again on a horizontal line where we put sample proportion value low on the left and getting higher to the right. So all sample proportion values are being placed on a horizontal line. Then some distribution shape of a sampling distribution of the proportion can be a multiple peak distribution shape like this. Or once again, after putting all sample proportion values from low to high on the left to the right, the distribution shape can come down to being a one peak distribution with possibly either a skewed right or in some other case a skewed left distribution. And it could also be in another case that once we put all values of sample proportions low to high from the left to the right on a horizontal line, then we can also find out that some distribution shape can become a one single peak nicely centered in the middle, and in a bell-shaped curve right here, we regard to this once again as a normal distribution. So any one of these possible distribution shape can happen to the sampling, to any sampling distribution of the proportion. And so as a bottom line, just like any other distribution of values, then this sampling distribution of the proportion also has three important characteristics. It will have a center, mu p hat. It will have an average spread that we call standard deviation of p hat value. But the usefulness of that, the meaning of that, is the average spreading. And it will have some kind of distribution shape. So how can we quickly calculate the mean, the center on this sampling distribution of the proportion, as well as how we can calculate the value of the average spreading, as well as how we can decide which distribution shape will happen on any of our sampling distribution of the proportion. Those will come in the following video lessons.